Hello and welcome to this video talking about the paper Active Diffusion Subsampling, which was recently accepted in Transactions on Machine Learning Research, where I'll cover some of the background theory and go through the algorithm itself with plenty of pictures and examples, hopefully help you understand the paper. So firstly, I'd just like to point out in the bottom right hand corner we have a QR code here which just links to these slides. So there's a few links throughout and text that you might be interested in. Firstly, I'll just mention a prerequisite that I'd recommend giving a read of, since this covers a lot of useful background information and we kind of build directly on this algorithm. So definitely recommend having a read of that if you haven't already. So now I just have a little agenda. So for the first half of the presentation or so, I'm going to cover some background theory that I think will make it much easier to understand the algorithm. And then I'll do a sort of step-by-step walkthrough of the pseudocode of the algorithm and just tie that to one of the diagrams from the paper and make sure that it's clear what's going on there. So if you're already comfortable with the background theory, feel free to skip to the second half. Okay, so first I'm just going to cover the general problem that we're trying to solve here, which is subsampling. So that's a situation where we've only observed some parts of a signal, but we'd like to recover the full signal. So you can see an example at the bottom here where we've seen some subset of the pixels, and our goal is to figure out how to fill in the gaps. This is also known as inpainting in the image community, but subsampling is a broad concept that can apply to any kind of signals. So audio, medical image data, any kind of signal really you can subsample. And in general, we think about having some budget of samples. So we might be acquiring like a quarter of the pixels, or every second measurement of an audio signal or something like that. And we also, for active subsampling in particular, which is what we're doing here, we can assume that we have some choice in how we can sample this signal or how we can subsample it. So we want to be able to choose the measurement locations rather than being given some predetermined sampling strategy, such as every second sample, for example, or something like that. And the motivation is simply to reduce the various cost factors associated with acquiring these measurements. So it might take too long, it might be expensive, or it might damage the subject in some way that you're trying to image or measure. Okay, so now we'll just talk about the mathematical model that we use. So we use Y to denote the measurements, X for the target signal, and then U is a subsampling mask that just selects certain elements from the X vector. There can also be a slightly more complex case, or the more general case here, where we also have some sort of measurement function or measurement model, and potentially noise as well. So in the case of MRI, the measurement model is Fourier transform, so it's a spatial Fourier transform in two directions here, and you can then subsample the frequencies in a certain direction, like in particular these vertical columns of pixels here. That's what you typically measure in MRI, and our subsampling mask can select certain frequency bins then to sample. The main thing that's important for this measurement model is just that it's differentiable, and then the method should work. And we also make the assumption that the noise here isn't dependent on the target signal, so that it's kind of independent. But yeah, those are the assumptions there, and this covers like a wide range of models. So yeah, next I'll just mention Bayesian subsampling. So this is the idea that because the problem is ill-posed, so there's sort of a many-to-one relationship between X and Y, in the sense that many different X's could satisfy this measurement that we've observed. It's nice to be able to represent that as a whole distribution over target signals and to preserve that uncertainty. So I represent that here as this prior distribution Px and this posterior, given these measurements, that kind of constrains the distribution. And when you have measurements like this that just give you more information about the target signal, that will have the result of constraining the distribution, basically decreasing its entropy. And that's an important topic that we'll come back to. So next, I just want to think about this case of sequentially measuring the target signal. So rather than getting a bunch of measurements at once and making some Bayesian update, we can imagine them getting them one at a time, in which case we sort of condition on more and more of these measurements as we go. And as you can see in this diagram on the right here, this has the effect of decreasing the entropy with the more measurements we get, or at least not increasing it, but typically decreasing in a case like this where it's like a natural image. And so we can use this idea of measuring the sort of size of that distribution, or the breadth or narrowness as entropy. And in particular here, we can actually turn that into an objective. And we can say, well, if we want to choose an intelligent sampling location that will give us as much information as possible, we should choose the one that minimizes the posterior entropy of our distribution. So in relation to the previous diagram, that would be choose the measurement location that will result in the smallest distribution or narrowest distribution once we measure it. And so that's represented here using this big A variable, which just represents a set of measurement locations. And so here we haven't like time indexed it yet and made it sequential, but the general idea is to pick some set of measurements A that will minimize this posterior entropy. And we also show that that's equivalent to maximizing the mutual information between y and x, or this is a result that's been shown many years ago, but we leveraged this in our paper. And now we time index it. So here the small at is referring to an individual measurement location. So we're back to this idea of sequentially sampling the measurements. And we're using this mutual information objective and saying, okay, let's choose the next sampling location to be the one that, when we combine it with what we've seen so far and using everything we know about the previous measurements we have, that we'll maximize the mutual information between y and x. And a good way to think about this mutual information is just how predictable x is from y, which is ultimately the goal here, is to sort of recover x from y. And you can manipulate this and show that it's actually equivalent to maximizing this term, which is composed of two entropies. So the first entropy here is the sort of posterior measurement entropy. So this is like if you've observed like k measurements so far, and you're trying to imagine what will happen in these new locations that you haven't measured yet, you can sort of measure the narrowness or the broadness basically of that distribution with this entropy here. And the sort of intuition for this is that if there's some location that you expect to be high entropy, so if you're trying to simulate what you'll observe there, but you're uncertain, that will actually be a good location to measure. And that's the first term. The second term actually cancels out. So this is because of the measurement model that we've chosen. So as I mentioned earlier, we have this assumption that the noise is independent of x and that the measurement model is otherwise deterministic. And so with a Gaussian distribution then, for example, on the noise, we find that this distribution given x is just a normal distribution centered around this measurement resulting from x. So that is, in the MRI case, for example, x would be this image of like some anatomy, like a knee, and y would be the Fourier transform of that. So this would just be a normal distribution placed on the Fourier transform of that knee image with some Gaussian noise. And of course, since it's just this deterministic function to map from the knee to its Fourier transform, the only entropy in this distribution is the entropy of the noise. And so this ends up being totally independent of AT, which is the variable that we're optimizing here. So this term just becomes a constant that we can cancel out. And then we're just left with this first term, and that's what we use as our objective. And just to visualize that a bit, to make it clearer, this is sort of the whole pipeline here. So I refer to this as generative active sampling, which is this case where we're actually going to approximate this entropy using a generative model. So this is some sort of conditional generative model that we can provide it with some measurements, and it can generate posterior samples for us. And in this case, we've got a model trained on MNIST, and you can see that it's gathering measurements over time of this unobserved target, and that over time it's getting these better and better posterior samples with a tighter distribution. And the entropy that we previously described comes in here in that we estimate this entropy from the set of posterior samples. So in this case, we could take just the variance as an approximate entropy, which is they're proportional under certain distributional assumptions. And if we were to plot the variance on the right here, you can see that at the start there's quite a lot of variance and it sort of shrinks over time. And the way that we sort of think about that objective that I mentioned previously, where we're trying to choose the measurement locations that maximize this posterior measurement entropy, is that we're just going to look at this entropy map and we're going to choose to sample the locations that light up the most. And so an intuitive way to think about that is if there's some region in the image that all these posterior samples disagree with each other in. So for example, at the start, there's a lot of entropy around here because, you know, maybe it's an 8 or a 9, and so some posterior samples have a white part there, others have a black part. That will cause some disagreement, and that will result in a high variance in that location, or a high entropy, as it were. And our objective tells us that's where we should sample. And so we drop a measurement location there. We acquire that from our target. We give that to the generative model, and then it can use that information to come up with better posterior samples. And this should lead to the minimum posterior entropy. So basically choosing the region of the measurement space that has the largest entropy should lead us to a posterior distribution on our target with the smallest entropy. And that's the core idea of generative active sampling. And that's what we try to implement using diffusion models in our work. So quickly, just to explain exactly how we approximate this entropy. So we don't actually use the variance, but rather we approximate this measurement posterior, as I call it, with a Gaussian mixture model. So that is, we get a bunch of simulated measurements. So here we're just using our current posterior estimates as simulations for what we would measure at each of the possible measurement locations for the 0. And each of those becomes a point in this measurement space, or a simulated measurement space, where we simulated the full measurement. And we center a bunch of Gaussian spheres on those, and we get a Gaussian mixture model. And the reason we choose that is because you can fairly easily compute the entropy of that distribution, which you can see here. So this term that we're trying to optimize becomes quite easy to compute. And you can see this looks kind of similar to a variance in the end, because we've got these squared error terms where we just look at the squared error between all the pixels here, and basically choose the measurement location with the largest squared error between the pixels. And that's how we measure this disagreement between the pixels in this case. The main difference between the variance then is that you have this sigma y term here, which determines the narrowness of these Gaussians. And so you can you have this hyperparameter that you can use to control the sensitivity of this entropy approximation to outliers, which can be useful. And so just to point on the notation here, so this AT refers to some possible action. That's why we use the letter A, but that is basically a measurement location in the measurement space. So for example, we might be, our possible measurements or our action space might be blocks of pixels like this. And so AT will be one such block. And in order to compute the entropy of this action, or the resulting entropy from adding this action to the set of actions we already have taken, and taking into account what we've already observed, we can basically compute in this location. So the set of pixels, which is denoted by L here, that are a member of this sort of action, we just sum across those, and then that gives us this entropy for that action. And so this is reasonably flexible depending on how you want to define your action space. So for example, in MRI, as I said, the actions there are like columns of pixels in the frequency domain. So then each AT would be some column index. These could also be overlapping or different shapes. It doesn't need to be some uniform grid, so it's reasonably flexible. It's just some way of splitting up the measurement space into different subsets of pixels. Okay, so that covers the background theory. I'll just finish that section with some shout outs to other interesting work on this area that I'd recommend giving a read. These papers use VAEs and GANs to do similar things, so if you're interested in that, take a look. And now I'll move on to our algorithm and how we implement this idea of generative active sampling in an efficient way with diffusion models. So I won't go into like an extensive background on diffusion models here because I think that's been done well before by many YouTube videos and blog posts. So I'll just link one blog post here. But the main important points about diffusion models that are necessary for discussing this algorithm are A, that they generate like state-of-the-art images and they just model distributions particularly well, which is very useful for solving these subsampling problems. And the other important factor is that they are relatively slow for inference compared to other methods like VAEs or GANs that have been used before for generative active sampling. So as you can see here, we've just depicted this reverse diffusion process of iteratively denoising these images. And this just illustrates that there are many neural function evaluations required to do diffusion inference. And that's the key problem that we try to overcome here. So the naive way to implement generative active sampling with diffusion models would be to infer a posterior for each measurement that you want to take and repeat that for however many measurements you need. So if you need 30 measurements, that requires running a reverse diffusion process 30 times. And if you need 1,000 measurements, same goes. And so that's not very scalable because you need maybe hundreds of calls to a UNet basically to do inference each time, and so that scales to say hundreds of thousands of UNet calls if you need to do like 1,000 measurements, for example. And so we tried to tackle this problem directly by leveraging the Tweedy estimates that you get during the reverse diffusion process, and these are computed already in order to figure out which direction the image should be denoised in, basically. And the definition I've provided here, it's basically the expected value of the fully denoised image, x0, given some partially noised image, x tau, where tau denotes how noisy it is at the moment. And basically, you could think about this as from some partially noisy image, we can imagine a bunch of different paths that we could take to get to a clean image that, if noised, would map to x tau. So it's another inverse problem. And so this expected value is kind of an expected value over the outcomes of all those different paths. And so if x tau is quite noisy and quite ill-posed, in the sense that x0 could be many different images, this Tweedy estimate becomes kind of blurry because it's an average over all of those. So that's sort of how you think about Tweedy formula and Tweedy estimates, and they will then sort of become less blurry over time. So I've got some visual aid here. So if we were to start at the very start of the reverse diffusion process, where we're just looking at total noise, what we'll get is a sort of average over our prior distribution, or an average over everything our generative model could generate, basically. If we give it some measurements or just let it generate itself, in this case, you can see, okay, it's decided on a path that will lead to a human face, but there's still some uncertainty around exactly what the face will look like. And so this just gradually deblurs over time into a crisp image. And we leverage these estimates as distributions, basically, to compute our entropies from. And from that, we can decide the measurement locations during the diffusion process, rather than having to wait till the end to do that. And while these aren't perfect estimates of the posterior, we find that they are good enough to identify good sampling locations that result in higher quality images and intelligent sampling masks. And that's basically the core idea of the algorithm. So in what follows, I'll just go over the pseudocode here to make sure that's clear and tie it to this diagram that we use in the paper to illustrate the process of a single sort of action selection or measurement location selection. So first I'll just start with all these variables that we require at the start. So we've got big T, which is the total number of diffusion steps. NP is the number of particles. So during this process, we of course need to generate multiple posterior samples in order to get an idea of the entropy of the distribution. And we refer to those as particles, which is an analogy from particle filters, which use a set of samples from a distribution known as particles to represent it. And so that's what NP refers to. Then we've got big S, which is our sampling time points, or in other words, this is the set of diffusion time steps. So some numbers between tau and big T, at which we want to acquire some new measurement and decide some new sampling location. So for example, if big T was 100, so if we had 100 diffusion steps, S could be, every 10th step if we want to take 10 measurements. Then we have the diffusion guidance weight. So this is just weighing it's kind of like a weight for our likelihood, which determines how strongly we listen to our measurements basically versus the prior. So if you're unsure what I mean by that, I recommend going back to the diffusion posterior sampling paper and taking a look there, because it comes from that. Then we've got our variances of our or standard deviation, of our noise that we add during the diffusion process for stochastic generation. Here we have our alphas, which are our signal rates, our initial actions. So this might be, in some cases, you might want to start off with some like manually selected measurement locations. So in the case of our fast MRI experiments, for example, we initialize with a measurement of the DC component of the Fourier transform, so just the center, like the lowest frequency component, basically. And in some cases, you might want to do this to just speed things up a little bit, because sometimes it's kind of obvious where the first sample should be. Next here, I'll just skip to the initial measurements. So the reason I highlight this is because what we're denoting here actually is acquiring a real measurement from our target signal. So this isn't to say that we're sort of simulating some measurement from posterior samples that we've generated, but rather we're actually acquiring this using whatever sensing device we have. So in the MRI machine, this means actually making the acquisition. And that's denoted by X, the target signal, rather than X with some superscript here, which is what we use to refer to our posterior sample particles that we're denoising. And then finally, we'll introduce this set of particles which start off as just these random Gaussian noise images. So now the first part of the algorithm is this sort of this for loop, which just iterates over each of the particles in our particle distribution, and it just does regular diffusion posterior sampling. So nothing special going on here. We're just calculating these Tweedy estimates, which we'll use later, and we're simulating these full measurements. And this is something that needs to be done anyway for diffusion posterior sampling in order to compute the likelihood, or the data fidelity step, as you see on line 9 there. But we also use these later to compute our entropy. And yeah, this is just the data fidelity step from diffusion posterior sampling. And then the part that sort of we add to the algorithm that starts to move away from diffusion posterior sampling is when we're in a case where tau is a time step at which we want to take a new measurement. And at that point, we will first compute our entropy using the Gaussian mixture model approximation that I described earlier. That'll give us some new measurement location. We then add that to our set of measurements, and we use that set to acquire our new measurements from the true signal of interest. So YT here refers to the set of all the measurements we've acquired so far, but in reality, if it's like some sort of sensing device like an MRI machine, we will just be acquiring this new measurement at A star T. And that's it. So that covers the the main pseudocode of the algorithm. We also have actual code on GitHub, which I'll link to later. But yeah, that's the main idea. So now I'll just show a GIF of this in action. So this is using stable diffusion with our algorithm ADS, and it's got a face from the CelebA dataset. And you can see over time it's sort of narrowing in on this distribution. And we use only 4 particles here, and that's actually already enough to derive reasonably informative entropy estimates and identify good sampling locations. Here are then some results. So here's just comparing ADS, which is designing, as you can see here, clever sampling masks on the left, and you can see that the sampling masks sort of identify informative regions that correspond in some way with the structure of the image, or in particular with areas of fine detail or distinction that might be important for ensuring like a good reconstruction accuracy. So for example, around the hair here, where there's a large difference in color and brightness between the hair and the background, and this results in like a high entropy in our entropy model. And compare that with diffusion posterior sampling here with random masks, we see that it often misses important locations, and that can result in uncertainty around those locations, which you can see as blur here, since we've plotted the posterior mean to sort of give some indication of all of the different posterior samples that you would get if you actually took, say, K samples from diffusion posterior sampling in this case. And that's all. So I'd just like to thank you for watching and encourage you to check out our GitHub if you'd like to implement this yourself or to play with it. We've got Docker images and model weights and everything you should need to get started. And if anything's missing, please let us know in the issues. Otherwise, yeah, thanks again for watching.